Hello everybody. Uh, let's start today's video. From where we left in the last session. So, the problem was the powder diffraction pattern of a BCC crystal is recorded by copper K alpha radiation of X-rays of wavelength 1.54 angstrom. Okay, now there are two questions. Question number one is if the plane is given, HKL is given, and who's diffracted at an angle of 60 degree, then lattice parameter is what? That's first question. And second question is assuming the atomic mass of constituent atoms to be 50.94 AME, the density of the crystal in units of kg per meter cube we need to find out. So let's start from the first problem. Okay, so yeah, so we have HKL equal to 002, and then lambda is also given. So lambda is 1.54 angstrom, and the 2 theta is given here, which is 60 degree. So yeah, diffracted at an angle 60 degree, because this looks like somewhat. So this is 60 degree. Okay, so the angle we need is theta equal to 30 degree. So theta equal to 30 degree. So we know 2d sine theta equal to n lambda. Nothing has been mentioned, means we'll consider first order peak. So now we know DHKL equal to A by, for a cubic lattice, H square plus K square plus L square, right? So A is the lattice parameter. So H square plus K square plus L square sine 30 degree equal to lambda 1.54 angstrom unit. So A will be 1.54 into root over 2 square plus 0 square plus 0 square, meaning 1.54 into 2 angstrom. And the answer is, this will be something 3.08 angstrom. Okay, so this is the correct answer. So option B. This was first problem. Now coming to the second problem. The second problem, we need to find the density of the crystal. So the formula that we know is density is equal to NMA by NA cube, right? So here mass is N is here, not to be confused with this order of peak, but N is here number of atoms per unit cell. Okay, and so sorry, the mass is NMA by Na. So Na is the Avogadro number, and Ma is the atomic mass, which is given here 50.94 AMU. So now given that BCC crystal we have, so there are 2 atoms per unit cell, right? For BCC body centered cubic cell. So 2 into 50.94 by A we know 3.08 into 10 to the power minus 10 cube, then Na. If we found this in SI unit, then it will be around 5.79 into 10 to the power 3 kg per meter cube. Okay, so yeah, so C is the correct answer. Moving to the next question. Okay, so the question is the X-ray powder photograph of a cubic substance taken with K alpha radiation, copper K alpha radiation. This is just to mention the particular wavelength, which is 1.54 angstrom. Shows diffraction lines at multiple Bragg's angle. For example, 12.3 degree, 14.2 degree, and 24.1 degree. Now we need to determine the Miller indices of all the lines, all these three lines, and size of the cubic cell. Basically, unit cell parameter A. Okay. So again, we will start with what you know. 2d sin theta equal to n lambda. So n equal to 1. Now d again dhkl is for a cubic lattice h square plus k square plus l square. HKL are Miller indices which we need to determine actually. So 2a by sin theta equal to lambda, right? So since we need to determine each KL and we are given theta and lambda, so A we don't know, each scale we need to determine for three different angles, theta 1, theta 2 and theta 3. So we can write this above expression as follows. So let's say sin theta equal to lambda by 2a. That means sin square theta will be lambda square into h square plus k square plus l square by 4a square, right? Now we have multiple sin theta. So the ratio, so for a particular theta 1 there will be a particular h1 k1 l1, a plane, right? Now for another theta 2 there will be another h2 k2 l2 and so on. And so we can determine h1 square plus k1 square plus l1 square is to, this is for theta 1 angle, h2 square plus k2 square plus l2 square. This is for theta 2 angle. Theta 1 is 12.3 degree. Theta 2 is 14.2, and then h3 square plus k3 square plus l3 square, right? This is for theta 3 equal to 24.1 degree. So the ratio will be from this equation 4a square sin square theta by lambda square, right? In this case theta 1 by lambda square, again 4a square sin square theta 2 by lambda square, 4a square sin square theta 3 by lambda, sorry, not lambda 3, lambda square. So sin square 12.3 degree is to sin square 14.2 degree is to sin square 24.1 degree, right? And that ratio comes out to be very difficult, 0.0538 approximately, 0. Okay, sorry, I missed a part actually. So here another theta was given actually. Okay, sorry for this. This was 20.4 degree. Okay, so 4 theta was given. So that will not create any problem for us. So that will be our theta 3 actually. Okay, so that will be a theta 3 will be 20.4 degree. And then there is another theta 4 which is last one, 24.1 degree. So this will be h4 square plus k4 square plus l4 square is to 4a square sin square theta 4 by lambda square, and this will be 20.4 is to sin square 24.1 degree. Okay, so this will be okay. So if we round this decimal things, so it will be around, so how do we do this? So let's say divide all this by first one. Okay, 0.060 by 0.04538 is to 0.125 by 0.04538 is to 0.1667 by 0.04538. Okay, so this will be around 1.1.33 is to 2.67 is to 3.67. Okay, now these things we can write as 1 is to 1.33 can be written as 4 by 3 is to 2.67 is around 8 by 3, 3.67 is around 11 by 3. So ultimately we'll get 3 is to 4 is to is 8 is to 11. So now what we need to do is these are the ratio of different h square plus k square plus l square, right? If you see from here now, so for which h square hkl combination, it will be 3 for the first case theta 1. So it can be 1 plus 1 plus 1, right? Because hkl are integer valued, we always express in that way. So the first plane we already got for theta 1. So h1 k1 l1 is 1 1 1. Okay, so this is one first plane or first line according to the question's language. Now we need to for h square find h square plus k square plus l square equal to 4. Right, so this can be multiple options is there. Options are there. HKL, so it can be 2 square plus 0 square plus 0 square equal to 4. Similarly, 0 square plus 2 square plus 0 square equal to 4, and so on. Right, but let's say first one we written H2 K2 L2 will be 200. Okay, this is second line. Similarly, there will be 8, right? So 8 again, 2 square plus 2 square plus 0 square equal to 8. Then 0 square plus 2 square plus 2 square equal to 8. So same. So we'll again first written the first one. H3 K3 L3 equal to 220. This is third line. And similarly we need to find 11, right? This one. So how do we get 11? So one option is 3 square plus 1 square plus the 4. 1 square equal to 11. You just shuffle them. 1 square plus 3 square plus 1 square is another option. So we'll again retain, sorry, just 11 first one. So H4, K4 and L4 is 311. Okay, so this is fourth line. So we got all the HKL of the four lines. Okay, now there is another question in the yeah, size of the cubic units. The size we can get from any of the information, right? So if you utilize this equation, we know the lambda. So let's say, so again 2D, let's use theta 1 only. Okay, theta 1 was 12.3 degree. Sin theta 1 equal to n was 1, so lambda equal to 1.54. Now each one k1 l1 we got. So 2a by root over 1 square plus 1 square plus 1 square sine 12.3 degree equal to 1.54, right? So from this we can find out a equal to 6.26 angstrom. Okay, so similar answer or the very close to this answer will come out if we use the information of theta 2 and corresponding h2, k2, l2 and theta 3 and so on. Okay, so this was the problem. Now let's move next problem. So next problem will be okay. Options are given as 2r 8 by 3 to the power half, b 8 by 3 to the power half into r, c 8 by 3 to the power 1/3 this time, and then r into again 8 by 3 to the power 1/3. So the question is, zinc crystallizes in HCP, hexagonal closed packed structure. R is the radius of the zinc atom. Now we need to find the height of the unit cell. Okay, so hexagonal closed brackets looks somewhat like this. It's very difficult to visualize. Draw actually. So there will be another A. Have hope. I'm not drawing fully, but yeah. So now there are two fundamental dimensions for HCP structure. One is C, which is vertical direction Z, and another is A, right, which is in plane. And the ratio for this is fixed. Sorry, C by A is root over 8 by 3. This can be proved with some calculations. Now, given that C is root over 8 by 3 into A, right? Now, the radius of the zinc atom is given as R, and A is this one, and there are sitting zinc atom next to each other. So, this will be 2R equal to A. Okay, so A by 2 will be radius of each zinc atom into A equal to 2R. So C is the correct option is 2R into 8 by 3 to the power half, right? So option A is correct. So let's move to next problem. Okay, so more square lattice. So options are B equal to root 2, b equal to 2, b equal to 4, and d b equal to 8. So the question is the kinetic energy of a free electron at a corner of the first Brillouin zone of a two-dimensional square lattice is larger than that of electron's energy basically at the midpoint of a side of the zone by a factor of b. Now we need to find the value of b. So for a solution, so first we need to know the Brillouin corner and the midpoint of a side, right? So let's draw the Brillouin first of a square lattice. Okay. So these are suppose y-axis and x-axis. So this is the Brillouin zone where this is along kx axis actually because it is Brillouin zone showing the reciprocal space. So these points are basically pi by a. If we assume this is a, this is minus pi by a. Similarly, this is also pi by a, minus pi by a, pi by a. So what is the corner of the first Brillouin zone? This is the first Brillouin zone. Okay, first Brillouin zone, Bridget. So the corner point is this one. This one is the corner point, right? What will be the coordinate? This is pi by a, and again this is pi by a. So the corner position will be pi by a, pi by a. Kx value is also pi by a, ky value is also pi by a. So this is the corner. And we also need to find for the second part midpoint of a side of the zone. So let's say this is the side of a zone, one of the side, and the midpoint is this one, right? This is again kx equal to pi by a, but ky equal to 0. So this is the coordinate of midpoint. And we know that kinetic energy of free electron E kinetic is given by h square by 2m. M is electronic mass, kx square plus ky square for 2d, right? So at the corner, what will be the kinetic energy? H square by 2m into, we know that kx at the corner is pi by a equal to ky basically, right? So pi by a square plus pi by a square. So this will be h square by 2m into 2 pi square by a square. Similarly, kinetic energy at the midpoint of the side is given by h square by 2m kx square plus ky square. This will be, this time kx is pi by a square, but ky is 0, right? So pi square by a square, and then the ratio is corner by midpoint. will be 2 equal to B. So this is the answer, B equal to 2. The correct option is B. Oh, just a second. So let's move to the next problem. Okay, so slightly different problem. Okay, so the question is short wavelength cutoff of the continuous X-ray spectrum from a nickel target is given 0.8 to 5 nanometer. Now, what will be the voltage required to be applied to the X-ray tube? Okay, so what will be the minimum voltage basically? So basically we have lambda equal to 0.825 nanometer, right? Then we can get the energy of the wavelength or of the X-ray. Energy of the X-ray E equal to, h nu equal to h c by lambda. Nu is the frequency and c is the speed of light. Okay, now this much energy at least is needed in terms of voltage supply. Okay, so this energy will be equal to EV. So V is the voltage, let's say, multiplied by the electronic energy, which amounts to energy. Sorry, E is the electronic charge. E and V amounts to electronic energy supplied by the voltage. So V will be E by small e equal to Hc by lambda into E, right? Hc by lambda into E. So if this H is Planck's constant, so 6.6 into 10 to the power minus 34. So light speed of light is 3.3 into 10 to the power 8 meter per second. Lambda is given as 0.825 into 10 to the power minus 9 meter into electronic charge is 1.6 into 10 to the power minus 19, right? So voltage will be 15.3 into 10 to the power volt. So we can write it as 1.53 kilovolt. So this much voltage is required. Okay. So the next problem,